So I want to thank the organizers and thank the Society of Catholic Scientists for inviting me and making this conference possible and working. I want to say talk about some formal aspects of science and religion and faith and science. Okay, let's skip it. First of all, some initial caveats. I do not intend to reduce faith to formal system. Nor I argue that the formal aspects of faith is most important. The same, by the way, applies to science a bit differently, but it applies also to science. It seems to me, however, that some results of formal logic can be relevant and inspiring for faith and science. So I will not be analyzing the reality or the set of sentences, propositions of religion or science or the methodology or philosophy of science. I want to concentrate on some results in logic that I think are important, relevant, and maybe also inspiring in our analysis or thinking about science and religion. I want to say a few words about my current and my own personal context, because you could think that I'm one of few theologians here who will speak from the theological point of view. I am a Dominican, of course, but actually my degree in theology is the lowest that I have. I mean, first I became a physicist, then I entered the order, and physics is still very close to my heart. And eventually, very recently, I did my work in philosophy in logic. So I want to share with you these experiences of my latest research. Okay, just a few words about the development of formal methods. At first, logic was considered a tool, an organon of philosophy. But with the scientific revolution, formal methods, mainly the mathematics, become even more important. And actually, the very title of Newton's work, Philosophiae Naturalis Principia Mathematica, is very telling. We could say that I have the feeling that Newton wants to convey to us that the real principles of the whole philosophy of nature can be best described as being mathematical. So the principles of nature are best described as mathematical principles. This is what he gives us in this work. In the 19th century, logic has begun to become independent and strongly developing. I proceed to set theory. First, I want to show you some important results. I guess you might know some of them, but let me remind it. I will rather skip very shortly. I will comment on it just now, but rather I will skip the profound Gödel's incompleteness theorems and their implications. The first incompleteness theorem states that no consistent system of axioms whose theorems can be listed by an effective procedure is capable of proving all truths about the arithmetic of natural numbers. And let me comment on it shortly. The theory of arithmetic is the really basic theory. I mean, there are much more bigger mathematical theories. This is the basic, that we want to just at least be able to count things, let's say, to be able to talk about numbers, natural numbers. So this is very basic. And actually, all the extensions of the so-called Robinson arithmetic or the Peano arithmetics is already an extension. So all the bigger theories, starting from the quite simple arithmetic theories, have this feature that if we want them to be in a certain way axiomatizable, and we want them to be consistent, they will not be complete. So there will always be some true statements that will be unprovable from the axioms. that was a big blow to the whole procedure of axiomatization. I will talk in a moment about it. The second incompleteness theorem shows that the system cannot demonstrate its own consistency. So maybe you heard about the Hilbert's program at the beginning of 20th century to axiomatize the mathematics, the different domains of mathematics, to give concrete axioms because there were some problems in set theory. Russell, for example, showed the so-called Russell's paradox, that the naive set theory is paradoxical, is inconsistent. So they were a bit afraid, okay, maybe the whole mathematics is inconsistent, let us do it rightly, let us axiomatize every domain of mathematics, and moreover, let us prove the consistency of these axiomatic systems. And these two theorems show that it is impossible to do so. It's really these are really profound theorems. I put them a bit on the side, but I was also thinking that maybe giving a lecture, like concentrating mainly on these. But let us deal with the reality of infinity for a moment. This is a passage from a letter from Georg Cantor, the author, let's say, of set theory, the first of the father of set theory, who wrote to a Dominican, Thomas Esser, "Thanks to my work, Christian philosophy has a genuine theory of infinity for the first time in history." He felt this profundity of the theory he was developing. And I just want to show you some results. We all know natural numbers, yes? 0, 1, 2, 3, ad infinitum. The notion of cardinality of a set is a measure of the number of its elements. So if we have a finite set, we can say there are 3 elements of this set, or 5 elements, or 1 element. The set of natural numbers is called countably infinite. There are infinite elements of a natural number set, but we can count them, 1, 2, 3. It goes ad infinitum, but you can count it. So, and this is the lowest, the smallest infinity in the set theory, the infinity, the countable infinity. And now we have a notion of equinumerous sets. I mean, we call 2 sets equinumerous if there is a one-to-one correspondence between them. I want to show you what does it mean. Look first at the top of the picture. If you have 2 sets, we have a function that gives to every element of this domain some element of this codomain. So every element here has a partner here, but there might be some partners that are not used, let's say, some values that are not used. This function is called the injection, but never mind. But different elements have always different partners here. This is one type of function. Another is that they might have different partner, but every element here has to be used, has to be a partner of some element here. If we impose these 2 conditions, so we want every element here to be used, and for any 2 different elements here, we get also 2 different elements here, this is what we call one-to-one correspondence. So just simply saying every element here has an element here, and different elements has different elements, and there is no element here that is not used. If there exists a one-to-one function between 2 sets, we call them equinumerous. For finite sets, this is obvious, okay? If one has 5 elements and the other is equinumerous, it also has to have 5 elements. But actually this works also for infinite sets. And it can be shown that the integers, so we add to natural numbers also negative numbers like -1, -2. The integers is also countably infinite, so it is equinumerous with the natural numbers. I think it's maybe it's not so obvious at the first point, but it's really easy to show the correspondence. But moreover, the rational numbers, which are, we could think, much bigger set, because between any two different rational numbers, there's another rational number that is between. So there's a kind of density, the set is dense. And it could be proven that the rational numbers are also equinumerous with natural numbers. So the cardinality of rational numbers is also countable infinite. But you know from school, from your education, that we can define, I will not define it, but I think you know what I mean, the real numbers. And it can be shown that the real numbers are uncountably infinite. So the number of the real numbers is really strictly greater than the any of countables of the number of countable cardinality of any countable set. And we can ask a question: is there any intermediate infinity between infinite cardinality of real numbers and the countable infinity? So we know that the countable infinity is the smallest infinity. We know that there is some infinity of real numbers that is uncountable, and the question is there any infinity between these two? Actually, this is quite simple to express this question. This is why I also chose to say about it. But this is a profound mathematical question. And this is connected with the so-called continuum hypothesis. Continuum is the cardinality of real numbers, this uncountable infinity. So the hypothesis states that there is no set whose cardinality is strictly between that of the integers and that of the real numbers. And the question is it true or is it false? Is there any set that has this cardinality between these two? And actually, establishing truth or falsehood of the continuum hypothesis is the first of the Hilbert's 23 problems presented in the beginning of the 20th century, which turned out to be really inspiring for mathematicians and scientists in the 20th century. This was the first problem. And the problem turned out not to be easy at all. In 1940, Kurt Gödel, one of the greatest logicians, showed that the negation of the continuum hypothesis cannot be proven in the standard set theory. I will denote it as ZF from Zermelo-Fraenkel axioms, but we don't have to go into it. So from Zermelo-Fraenkel axioms, we cannot prove this sign just means this. We cannot prove the negation of the continuum hypothesis, provided that the Zermelo-Fraenkel set theory is consistent, because as I mentioned, the second incompleteness theorem by Gödel showed that it also applies to Zermelo-Fraenkel set theory, that you cannot, within this theory, even you cannot prove its own consistency. So provided that it is consistent, we cannot prove, because if it is inconsistent, then everything follows from it. So this means that continuum hypothesis is consistent with axioms of, let's say, standard set theory, because we can add this axiom to this, and there will be no inconsistency because we cannot infer the negation of it. However, and this is another thing, I want to stress that these are two different things that need to be proven. Only in 1963, Paul Cohen, and on the side I can add that he received a Field Medal for this, which is corresponding in mathematics like a Nobel Prize, but even harder to gain because it's like 1 in 4 years given, and you have to be before 40, as far as I remember. So he showed that not only the negation of continuum hypothesis what showed Gödel, but neither itself, the continuum hypothesis, cannot be proven in standard set theory. And thus, it is independent of set theory, provided also that this set theory is consistent. So this is some results in mathematical logic in set theory. And yeah, just a comment about our attitude to it. It can also, of course, vary from person to person depending on our philosophical beliefs. Because if one is a Platonist, he could say, for me, the continuum hypothesis is either false, or true, independently of this unprobability from the axioms of set theory. But this is just one possible attitude to it. I just want to share with some possible connection of this with faith. This will not be really strong, but when I was reading St. Thomas Aquinas, some passages I felt about this correspondence with these results. So Aquinas wrote, certain things that are true about God wholly surpass the capability of human reason. For instance, that God is three and one. And other truths about God can be achieved within the natural capacity within the capacity of natural reason, but there are also certain things that are true about God which wholly surpass the capability of human reason. However, as we saw, things surpassing the capability of probability are fundamentally present even in set theory, considered by many as a foundation of mathematics. And moreover, as I mentioned, this phenomenon can be seen as genuine in mathematical logic under certain assumptions, as the incompleteness theorems show. So we have, even in mathematics, even in so simple, we could say, theories, formal theories, formal systems, we have this kind of phenomenon, let's say. We can ask whether can that which surpasses our reason appear to us in seemingly incompatible aspects without being contradictory in itself or to another rational being superior to us? That's a quite easy question, I think. And of course, we can give a very simple example, like going into third dimension, that certain three-dimensional object can be perceived. But imagine that we are like just the two-dimensional beings, and we just perceived everything just two-dimensionally. So we could think, okay, something seems to be like a circle or like a square, but of course it could be hard to compatible these two, but we can easily think that there is some bigger, let's say, object that we cannot perceive, which just shows in this way. You can even get the three different shadows. So the above very easy examples show that something superior to us, which is non-contradictory, can manifest itself in reductions or projections, which may not be easily compatible. This is a very simple example. However, sometimes it is also possible to show, because it is different to have problems with compatibility, and it is another thing to show that something is contradictory. So sometimes it is possible to show inconsistency of certain object. Like, for example, the so-called Penrose triangle. An object that is here depicted in 2 dimensions that can be proven to be impossible. So there's no 3-dimensional object that could look like this. And I just to wake you up after the lunch, that actually in Australia, there's one such object. And you can think how it could happen. So I just show you the picture from another angle. It looks like this. Okay, so a simple observation comes to mind. It is one thing, I just repeat this one thing, to prove a contradiction of something, and another to have the difficulty or even impossibility of showing that given assertions describe some single, possibly inaccessible reality in different respects. And a quotation from Aquinas that is somehow connected, I think, with these considerations, Therefore, in order to deduce the first kind of truth, the one accessible by natural reason, we must proceed by demonstrative arguments by which we can convince our adversaries. But since there are no such arguments in support of the second kind of truth, exceeding natural reason, our intention must be not to convince our opponent by our arguments, but to solve the arguments which he brings against the truth. Because as shown above, natural reason cannot be opposed to the truth of faith. So I thought this is somehow similar. So like this continuum hypothesis, it is different to show that we cannot prove it. And it is different to say we cannot prove its negation. And thus, if someone gives us a proof of the negation, we say there is some error in this reasoning. And also, for example, we cannot prove that it is possible in reality of God that he is three and one, of course, in different respects, but let's say this is a truth that surpasses our natural reason. But at the same time, we say it is not contradictory to reason. So if anyone gives us a proof that it is not true, we should be able to show an error in this reasoning. I think that's what St. Thomas wants to say to us. Okay, now I want to share with you with just some glimpses of category theory and logic, because my recent work was in category theory and some logics connected with it. And I think it really shows us some new aspects of mathematical theory called category theory. So category theory is a remarkable, relatively young mathematical theory that plays an important role in mathematics today. Its origin can be traced to the work of Samuel Eilenberg and Sanders MacLean from 1945. And actually Samuel Eilenberg is a Polish thread in the development of category theory. He was a Polish Jew. He defended his PhD in mathematics at the Warsaw University. Then he moved to Columbia University and did his research in US. Just a few general sentences about category theory. Apart from its relevance for mathematics itself, mathematical logic and philosophy of mathematics, category theory has more and more applications to physics. Also in quantum physics, there are works that try to figure out the nature of quantum theory from the perspective of category theory, especially topos theory, computer science, and in other disciplines. There's also a book by Ellen Landry, Categories for the Working Philosopher. So there are really many applications of category theory, not only to mathematics itself, philosophy of mathematics, or computer science, physics, but also for a philosopher in a wider sense. Category theory changes the way we think about the role of logic in mathematics, especially topos theory. And the topos is just a category that has some additional conditions to fulfill, so very more complex category. A topos theory gives us a whole bunch of universes of mathematical discourse, each with its own internal logic. I cannot describe in full, of course, what is a category theory, but it is much more concentrated on some structures. So a category is let's say, a collection of some objects and some arrows or morphisms, very abstract things between them, and very few axioms imposed on these notions, especially on these morphisms. So what is mostly important are not the objects itself, but the structure of between these objects. And it turned out that if we define a lot of notions in category theory, certain complex categories as known as toposes, we can define the whole logic there. And this is really an internal logic. We can we can decipher this logic. We can look for the structure of the arrows and see what is the logic of the topos. We do not impose it, but at the same time, every topos is a certain universal, it can be used in certain sense, alternatively to the set theory. So a lot of mathematics you can do in every topos, and it has its own logic. There's also very startling intrinsic connections between geometry and logic within topos theory. The logic of topos is known to be intuitionistic logic. Intuitionistic logic, okay, can be defined as a classical logic without a principle of excluded middle. So P or not P. Usually, in classical logic, this is an axiom. We say this is or a tautology, but here this is not an axiom. And just to show you, it was connected with some Brouwer and his philosophy of mathematics, and then formalized by Hating. Okay, the everyday example is that this is another. If we add this axiom to axioms of intuitionistic logic, we get classical logic. So we can add either principle of excluded middle or this double negation axiom. And the everyday example to show you that the intuitionistic logic is not as far from our daily life. If someone asks you, that's not a strong example, but if someone asks you, would you go with me tomorrow for a walk? And you say, I'm not saying not. It doesn't mean yes. And at the same time, it's very, so our language, the double negation in our language doesn't always work as a identity. Yeah? So double negations sometimes do something different than just nothing. And this is, in classical logic, this is equivalent, double negation is equivalent to a certain statement. And in intuitionistic logic, it is not. And actually, there's a very nice example of infinitesimals, so like infinitely small numbers, such small numbers that the square of a number is equal 0. So in real numbers, like in standard, in classical logic, if the square of a number is 0, then it has to be 0, okay? But here we can say it is indistinguishable from 0, so it is not different than 0, and being different meaning is not equal 0. So this is not equal 0, and in classical logic it means it is 0. But here in this logic, it doesn't have to mean that it is. So it can be indistinguishable from 0, but it is not 0 at the same time. So when we change logic a bit, we can get some different entities, let's say, in mathematics. Okay, the last part I want to concentrate on some conflicts that can emerge. So in general, conflicts could be threatening to us in everyday life, of course, but also contradictions are threatening to our reasoning. It is obviously not without cause that the principle of non-contradiction has long been so strongly regarded as one of the foundations of rationality. However, conflicts may be, or even are, also crucial to the development of a human being in general, in relation to other humans, and also in relation to God. I think every one of us has this experience that some conflict is really hard sometimes, but it can give us some new level of new development in our relation to someone or to God. It can also be crucial to the development of sciences, both in formal sciences, like in mathematics, as I said, with Russell paradox, for example, has been gave the development for the formal mathematical theory of set theory, as well as in natural sciences, like in LHC, in CERN, the physicists search for new physics. So they search for something that would be from the experiment that would be incompatible with the theory. Yeah? And we look for it because that would be something important, something that could lead us to some new physics. Of course, of arts also, development, also of our understanding of the scripture and God in general, like in St. Augustine when he says that some physical theories, like from sciences, can contradict if it contradicts certain interpretation of a scripture, and it is sure, then maybe we should change the interpretation of the scripture. Maybe we didn't understand something in a good way. So conflicts could be also good. Okay. This may come as a surprise to us, but in its diversity, logic and also it can also handle situations where contradictions arise, at least formally. A theory is called inconsistent. I already used this notion, but here you have the formal definition. If for some formula we can deduce or inference the sentence, the formula, and its negation, then we call this theory inconsistent. The theory is if it is not inconsistent, it is called consistent. And just another notion of a triviality. A theory is trivial if everything follows from it. Otherwise, it is non-trivial. And now we have a question, if there could be theories that are non-trivial, but at the same time that there are contradictions in it. And we call logic a paraconsistent one if its logical consequence relation, so the way we can infer from some sentences on other sentences, if it is not explosive. So it means that the paraconsistent logics could be used as the basis for inconsistent but non-trivial theories. So we have some kind of inconsistency in the theory, but it doesn't make the system explode. So it doesn't make that everything follows from it. In classical logic, if we have a contradiction, then everything follows from it. So this is like an explosion for a system, formal system. But it could be shown that there are formal systems, formal logic, called the paraconsistent logics, that you could have contradiction. So the principle of non-contradiction could be not fully existed there, and then the system will not explode. And there are plenty of paraconsistent logics. One of the first, if not the first one historically, was the so-called discursive or discussive logic proposed by Polish logician Stanisław Jaśkowski in 1408. He said, when two people discuss and we just put all the statements they say or have in mind, like in one set, there might be inconsistency in between them, the contradiction, because one could say something a P and the other say non-P. But at the same time, it's not true that everything follows from this discussion. No, it's not true that they could say any statement is true or false. No, these contradictions are somehow bounded. They do not explode. And he gave a certain logical system for it. So I think inconsistencies could be danger. I mean, there are some people who say, yeah, the world is inconsistent, the inconsistencies are true. My attitude is that they emerge in our life. That could emerge in the science itself. Like you can think about the particle wave duality. Yeah? For some time, the same, let's say, electron showed to be a wave in certain experiments, and in other experiments it showed to behave as a particle. So you could say this is contradictory. We need some time to go deeper down and to see the quantum level, let's say, which behaves in these different ways. Also in faith, we could have some contradictions sometimes, but of course we believe that there are no true contradictions. So these could come from our limitations, let's say. And also it could be true for this whole dialogue between faith and science. So in this context, I wanted to share with you that even logic can deal with contradictions in this way. So my philosophical attitude towards the inconsistencies is similar to Perzanowski's. This is one of the professors. Inconsistencies must be examined, not prejudged, nor worshipped as idols, as in the case of most Hegelians. Quite the contrary, we examine them in order to find a remedy, in search of the understanding about their sources, reasons, and real consequences. And conclusions. Formal sciences have a unique beauty and profundity for those who cultivate them. I think they also show some truth about God, about Logos, even the formal systems itself, like if you just study these beautiful theorems, for example, like the Gödel theorems, there is some profundity in it. Perhaps even they show some truth about God inaccessible with other tools. It seems impossible that they do not have the potential to describe or guide reflection on both faith itself, science, and their relationship. The new results of mathematical logic, as well as the extraordinary richness and diversity of logics, are astonishing and thought-provoking. And just two quotations. Michael Herro wrote, "Mathematical tools are much richer than our everyday intuitions and purely verbal distinctions. They are able to reveal unexpected aspects of reality." And Aquinas wrote, "Although our view of the sublimest things is limited and weak, it is most pleasant to be able to catch but a glimpse of them." Thank you very much.
Thank you. Any comments or questions?
So I have a question about the relation between infinity and some classical arguments for the existence of God, especially those from Aristotelian and Thomistic tradition, because all those, or majority of those arguments, they are based on the assumption, the premise that the actual causal regress ad infinitum is impossible. And some, non-believers, they deny this argument because they say that even though we cannot imagine regress ad infinitum, it doesn't follow that it's not real. It can be such possibility. So firstly, what's your approach toward such objection? And secondly, how would you classify the entire issue of infinite regress? Is it the realm of natural reason, or is that second realm beyond the natural reason, what Aquinas said about?
Mm-hmm.
Thank you.
So maybe I start with the second one. I think everything that we do, like the arguments from the causation, from the sequence of causations, this is within our natural reason. The truths that are beyond our natural reason are the truths that are revealed by God. And actually, Aquinas says that some of them which are revealed are still accessible to our reason, and there are reasons that God revealed them by nevertheless. So these arguments, I would say, they are within the natural reason. And as for the first question, I have the feeling that this is a different aspect. So here I was talking about some sets of elements that at least, but there are mathematicians who do not like set theory because of these, because there are infinitely many infinities. You can go on and go on. I just told you about the first one, the countably infinite. Then there's this continuum, and the continuum hypothesis was about the possible infinity between them. But there are infinitely many infinities. So people think this is too much, maybe. Like these axioms are too strong. So I just was talking about some results in certain theory, mathematical theory, the set theory, and especially the Zermelo-Fraenkel set theory. And the reason about the causation, about the sequence of causations, and the infinity of the sequence, I think it is something different. I have also some kind of strange feeling about these infinities, but at the same time, I mean, in principle, I guess we can imagine perhaps an infinite progress. So I think you would need another argument to say why it is impossible to have an infinite progress. Actually, one of our brothers in Warsaw, now living in Warsaw, he's just finishing his PhD in philosophy about these arguments about infinite progress and causation.
You gave as an example, and I don't know how seriously you meant the example, of something where it seems to violate the law of excluded middle. I'm not saying that I'm not going on a walk with you tomorrow. and that doesn't imply I will go on a walk with you tomorrow. But is that really an example of a failure of the law of the excluded middle? Because it seems to me it's two different things to say, I am saying that it is not true that P, and I am not saying that it's true that P. They're different statements.
Okay.
So saying, I am saying that it's not true that I'm not going on a walk is not the same thing as saying, I am not saying that it is true that I'm going on a walk. It seems to me those are two different statements, right?
Okay, I agree. That example was a bit humorous, I would say. The whole intuitionistic logic, which doesn't use a principle of excluded middle, comes from Brouwer's philosophy of mathematics. And he said, maybe that would be a better example. In his philosophy of mathematics, if we prove certain statement, it is true. If we prove that certain if we prove that certain statement is false, it is false. But if we are unable to prove either of these, and there are cases like this in mathematics, he said, for me, it is neither true nor false. And then one of his students, let's say, formalized his ideas, his philosophy of mathematics, and eventually get to the axioms of intuitionistic logic. So this is maybe a better example, but yeah, I agree.
Any more comments or questions? So maybe I can ask one about the continuum hypothesis. What if I ask a question, can I construct a set that has such property? Does the statement that you mentioned, that you cannot determine the actual hypothesis, whether it's true or false, tell me that I cannot construct it? Because if I could construct it, then it would automatically say that that it's correct.
No, but if you, because it is the continuum hypothesis is how is the name? It is independent of the axioms of Zermelo-Fraenkel set theory. It means you could have it as true. You could add it to the axioms as another axiom, but you could also add it as a negation of it to the axioms, and you will not get an inconsistent theory. So there are models for which of set theory, some models that could have this statement true, and there are models that could have this statement false, but not every model of the set theory have this feature, because then it would follow from the axioms.
So it means that you need to add something to the standard set theory to just be able to construct it, right? You cannot construct, because if you could construct it in standard set theory, then it would be compatible.
It is compatible. I mean, it is not inconsistent with the set theory, so you can add it.
If you can construct it, then the opposite would be incompatible. Right? So if I have an example and I say, okay, it exists, how can it be incompatible? It must be compatible in that case.
Yeah, I'm not saying it is incompatible. There are models, you can construct it, the models that have the continuum hypothesis true. And there are also models that have it false. So, but if you, so you cannot prove neither.
Let me rephrase. If I have a model where I construct it, as you say, and I have this model, the set that is constructed, what is the status of this set in a set theory without these additional assumptions? No?
I don't understand. If you construct, so because if you want to prove that the continuum hypothesis follows from the axioms, you can prove it either syntactically or semantically. Semantically, on the level of models, you have to say that you have to show that every model in which all the axioms are true has also certain property. And then this property would follow from these axioms. If every model have this property also. If just you could construct a model that has this property, then it means this property is not inconsistent with the axioms. But at the same time, it is not saying that they follow from these axioms always. Okay.
We can discuss over coffee break.
If I understand good, and I'm not wrong.
Let us thank Father again, and
Thank you
all
very
the
much.
speakers of the session.